All right, next couple examples, we're going to take a look at applying this new theorem, the divergence theorem, which is a really quick way to show that a series diverges. It's something that oftentimes gets kind of forgotten about. It is a useful tool. So what I would recommend is if in the future you find yourself trying to determine whether or not a specific series converges or diverges, and it feels like you're missing something, like you have tried every test at your disposal, like it's not geometric, it's not telescoping, it's not harmonic, you're having trouble with it, try the divergence theorem. A lot of times this is a theorem that, it just gets overlooked, and don't spin your wheels in the mud for a long time. If you've had some trouble, try the divergence theorem. It may very well be the key thing you need to figure that problem out. So the basic idea behind the divergence theorem is that if you're adding up pieces that they're not decreasing in size to 0, then your series will diverge. Okay? So for instance, let's take a look at this series 2n over 3n plus 1. Okay? So if we take a limit as n goes to infinity of the series general term 2n over 3n plus 1, we get the limit is 2/3. So essentially what this means is your series here, if we listed out its partial, or if we listed out its terms explicitly, so for instance 2 over 3 plus 1, 3 plus 1, so this would be 4. So 2/4 plus, for 2 this would be 4, 6 plus 1 is 4/7, plus for 3 this will be 6, and this will be 9 plus 10. So we're adding 3 each time to the bottom. Okay. And then we're adding 3 to the bottom. So this is 8/13 plus 10/16 plus 12/19, so on and so forth. Now, if you actually look at these terms, so you have a half reduces, and then we have 4/7 plus 3/5 plus 8/13 plus 5/8 plus 12/19, so on and so forth. And if you look at decimals for these, so this is 0.5, this 4/7, that's a nasty one. This is 0.5714. I'm just going to round to the nearest 4 decimal places. I don't need anything more than that. Plus 3/5, so that's 0.6. Plus 8/13, this is 0.6154, again rounding to 4 decimal places. Plus 5/8, 0.625. Plus lastly, I'll do 12/19, which is 0.6316, again rounding to 4 decimal places. So 2/3 as a as a decimal, of course, is 0.6 repeating. So 0.66666. So now I only went down to the term n equals 1, 2, 3, 4, 5, 6. N equals 6 was the term that I used right here. So not that far down the list at all. This limit is when n goes to infinity. This expression here as a decimal will approximate 0.6 as a decimal. So even after just 6 terms, I have 0.6316. So again, this is not exactly 0.67, but as you can see, the further we go in our series, the number that we will be adding is getting closer to 0.67. Okay? It will be. So, essentially what this means is since we're going to be doing this for infinity, we're going to be adding this up forever, infinitely many of these terms. If almost all of them, if all but finitely many of them are virtually indistinguishable from 2/3, then adding up 2/3 an infinite number of times gives you what? Infinity. These numbers are getting bigger. So that's exactly what's happening. We need, for the divergence theorem, we need the limit of the expression that we're adding up, our general rule. We need the limit of that as n goes to infinity to be 0, because we need our terms to get small enough quickly enough. So you don't need to do all this work down here, but the basic idea is not that far down the series, the terms basically become indistinguishable from 2/3. And if we add up the number 2/3 an infinite number of times, we're going to get infinity. So the fact that this is not equal to 0, this implies this series from n equals 1 to infinity of 2n over 3n plus 1 diverges. And again, we can always be more specific and say diverges to infinity. That is an excellent habit to be in. Okay, determine if this series converges. So since we're talking about the divergence theorem, you might think to use the divergence theorem. So if we use the divergence theorem, 1 over e to the n, we get that this limit is 0. So although this limit equals 0, this doesn't imply that the series that we have converges. So what's important here for this divergence theorem is that the converse is not true in general. What does that mean? It means that just because you take the limit of your series term and you get 0, that does mean your terms are getting smaller and approaching value 0. That doesn't mean that your series must converge, because remember, we've got the harmonic series. So the counterexample here is that the harmonic series of 1 over n from 1 to infinity diverges. That's the counterexample. The limit of 1 over n as n goes to infinity is 0, yet when you add up these terms, that series does equal infinity. It diverges to infinity. So a lot of times when you're working on the divergence theorem, a common misconception is if you get the opposite result, instead of not equaling 0, you get equals 0, you also want to flip the conclusion. So instead of not equaling 0 and diverging, people want to say equaling 0 implies convergence, and that's not true, and you can always think of the harmonic series. So that's why the harmonic series is such an important series, is it is a really critical counterexample to something that's extremely non-intuitive. Okay. This series does converge, though. It's just we can't show it using the divergence theorem. So this is sort of a separate little fact to keep in mind. Okay, it's sort of like a little aside. This series does actually converge because I can write it as 1 over e to the n is geometric. And 1 over e is the common ratio. And that is less than 1. So we get convergence. So this series right here converges to the first term, which is 1 over 1 minus 1 over e. So this converges to e over e minus 1. Example 10. Determine if the series of 1 over n from n equals 1 to infinity converges. Well, this series here is the harmonic series. And we proved in example 7 that it diverges. So it diverges.